Okay, so both of these are a little bit different problems for us. Let's start with the cone over here. For the volume, in fact, whether we're finding volume or surface area, the first thing we always have to find is the area of the base. The base of this is a circle, so the area is pi times the radius. So it's not going to be 22, it's going to be 11 squared. So 3.14 times, oops, get back there, times 11 squared, 379.94. And that's going to be square inches. So the volume is area of the base times the height, which is 60 inches. But since this is a cone, what do we have to do? Divide by 3. It was 7598.8. 7,598.8 cubic inches. Anybody have that for the volume? Okay. Yeah, that's the same as this number here. For surface area, we also need the area of the base, 379.94. This is a cone, there is only one base, so we only add it in once. We need the lateral area to add to that to get our total. To find the lateral area, we need two things. We need the perimeter of the base. That's a circumference, so that's just going to be pi times the diameter, pi times 22. So 69.08. The other thing we need, since this is a cone, remember the length of this lateral side is not just the height, it is this slant. So we have to find that slant. So if I draw in this triangle here, this is the radius, that's 11 inches. This is that height of 60 inches. We're looking for this. What's that? So this is going to be 11 squared plus 60 squared equals that slant squared. If you do that out, this becomes 61 inches. So then the lateral area is the perimeter of the base, 69.08 inches, times that slant of 61 inches. And since it forms a triangular shape, it's divided by 2. $2106.94 inches squared. That's our lateral area. We add those together. Get our total surface area. Anybody come close to that? Any questions on that problem? Well then, it's fair to move on to the sphere over here. Anybody remember the volume of the formula for the volume of the sphere? Cubed, right? This is 4/3 times pi times 9 cubed. So 4 divided by 3 times 3.14 times 9 to the power of 3. 3052.08. cubic inches. That's it for the volume. How about the formula for the surface area? Surface area is 4 times pi times radius squared. So 4 times pi times 9 squared, which is what? 1017.36. Does that look right? Close enough. Any questions? What if I have a cylinder that is diameter of 16 inches, height of 20 inches? Find in your notes for me the volume and the surface area quick. Let's check the volume first. I'll give you a little more time to finish up the surface area. For the volume, no matter what we're finding, volume or surface area, first thing we have to find is the area of the base. This is a circle, so that'll be pi times radius squared, so pi times 8 squared. That's a diameter of 6, that's going to be a radius of 8 inches. Pi times 8 squared is what, 200.96, I believe, inches squared. So the volume, 200.96 square inches times a height of 20 inches. (4,019.2 inches cubed, look correct? Okay. I'll give you a couple more minutes to work on surface area to finish that up. So once again, we start out with the area of our base. Unlike the cone, however, this one has two bases, one on bottom and one on top. So we do have to add it in twice. And then we need our lateral area. So to figure out our lateral area, we need two things again. We need the perimeter of our base, which is just going to be a circumference. So that's pi times the diameter, pi times 16, which would be 50.24. And the height, we don't need to calculate a slant because on a cylinder the sides go straight up, so that slant is just the same as the height. So our lateral area is 50.24 inches times 20 inches. Do I need to divide by 2? Say no. No. Oh, very good. So it's 1,004.8 square inches of lateral area. So that adds up to be 1,406.72 square inches for total surface area. Anybody get that? Close? Rounding error? Oh, gotcha. 50.26 is you use the pi key on your calculator as well, so that's acceptable. Okay. This is just the same cylinder. I'm redrawing it so it's on the page. Here's what I want to do is I want to shrink this cylinder. So its diameter is now 12 inches. What's that height going to be? Well, I shrink it if I'm assuming I'm just going to do a reduction of it, meaning it's proportional in all directions. We talked a little bit last class about two-dimensional objects like triangles. This is a three-dimensional object, but it works the same. 16 became 12. So we have the 20. Is that going to go on top or bottom? It goes on top because it's from the same figure as the 16. So that missing height on bottom here, how are we going to find it? 12 times 20 is 240. Divided by 16 is 15. The height is 15 inches. Let's cross multiply and divide in the proportion. To find the surface area without having to calculate it, we have a ratio of lengths here. The 16 over 12. In fact, if I wanted to, I could reduce that to 4 over 3. Both of those can be divided by 4, right? I'm not going to put that there. I'm going to put that up here. So it's a 4 to 3 ratio of lengths. So a surface area is just an area. What would my ratio of areas be? Remember what we have to do to our ratio of lengths? Square it, yeah. 4 squared is 16. 3 squared is 9. So the ratio of areas is 16 to 9. So I had the surface area before I reduced it of 1406.72. I can cross multiply and divide there now. It's 1406.72 times 9 divided by 16. 791.28. That is going to be inches squared is the surface area of that reduced figure. I can just get it right off of the ratios. How about volume? Well, 4 to 3 is still my ratio of lengths. What am I going to do to those to get a ratio of volumes? Well, we're going to cube it. Volumes are three-dimensional. 4 cubed is, 4 times 4 times 4 is 64. What's 3 cubed? 27. Very good. So my ratio of volumes is 64 to 27. So the volume I had calculated for that was 4,019.2. After it was reduced, cross multiply and divide. 4,019.2 times 27 divided by 64. 1695.6. That's cubic inches. Does that all look kind of vaguely familiar? So you can see those ratios are very powerful if you need anything large or reduce anything like that. So let's say these are what we call similar figures. Similar figures means one's a reduction or enlargement of the other. These don't look much like it, but pretend. So let's look at this one. We need to find missing pieces. But first thing we need to do is match up the pieces that correspond from one figure to the next. So we start with the 12 here. What does it correspond to on the other one? Careful. The 8. It's between this point here and the lesser angle. Yep. How about X? What's that correspond to? The 4. Very good. 9. Because I asked. It goes to the Y, you're right. And Z corresponds to 10. Well, looking at those pairs of corresponding sides that I have connected, I need to find at least one that has both numbers. Do we have that one anywhere? 12 and 8 has both numbers. So I know I have that relationship of 12 to 8. I make that a ratio. Now, let's say I want to find X first. Where does X go in this other proportion? On top. How do I know it goes on top? Exactly. It comes from the same figure as the 12. What's going to go below it? 4. Why the 4? Yeah, it's the corresponding side from the other figure, and 4 is from the same figure as the 8. So to find X, we cross multiply and divide. So 12 times 4 is 48, divided by 8 is 6. So X equals 6. Okay, so for finding Y, we still got the 12 over 8. So we still have the 12 over 8. Where's Y going to go? It's going to go on bottom because it's from the same figure as the 8. What goes above the Y? The 9 is the other corresponding side from the other figure. And we'll cross multiply and divide. 8 times 9 is 72 divided by 12. Y equals 6. How about Z? Okay, we got 12 to 8 again, and Z does go on top from the same figure as the 12. What goes below Z? 10 is the corresponding side from the other figure. And we cross multiply and divide. 12 times 10 is 120 divided by 8. Z is 15. Are these triangles similar?
No.
How can we tell if they're similar?
The line is looking like it's closer to a right angle on one of them than it is on the other.
Well, you have to trust the lines though. The arcs are, the double arcs tell us that this angle equals this angle. And the single arc tells us that angle equals that angle. If those angles are equal, what does it tell us about this third one? They have to be equal as well. If 2 of the 3 angles are equal, the third one has to be. If all 3 angles are equal, then these triangles are similar. Let me change that just a little bit here. In your notes, find X and Y for me quick. So we need two sides that are corresponding that we know the length of. Which side would that be? 22.5 and the 10. 22.5 goes to 10. So to find x, where's x going to go? Top, and on bottom of that would be the 8 is its corresponding side. Cross multiply and divide, we get x equals, what is it? Perfect. 18 for x. Keep the 22.5 over 10. Where's y going to go? On top, still from the same figure. What goes below y? 10. Nope, 4. Sorry. I should listen. And we cross multiply and divide. 22.5 times 4 divided by 10 is 9 for y. Any questions on those? Okay. So the big concept for today is a lot of times in math and in nature there are numbers that are linked together. The time you spent working and the amount you're going to get paid. Your height versus your weight. Time spent studying and the grade you earn on a test. There's all sorts of numbers like that that are linked together. We refer to them as an ordered pair. We can express them just as a pair of numbers. Let's say 2 and 7 go together. Now these represent different values. This first one is what we're going to refer to as an x value. The second one we're going to refer to as a y value. Now if this were like data analysis or a statistics course, this would be referred to as the independent value and the dependent value. Independent just means you can pick whatever value you want for it within a certain pool of numbers. The dependent value says once you pick this one, it influences what this one's going to be. That's the whole point of having them linked together. So there's some sort of relationship. One number does influence the other one in some way. Well, to show them linked together, we got to go back to how we represented individual numbers. We had a couple of different ways of representing our numbers on a number line. 2, we represent it with a vector like that. That's more of an operational representation. If you're going to add, subtract, multiply with it, that works better. But the way for just representing the value itself, there's just a dot at 2. So I can represent the 2 and I can represent the 7 real easily like that on a number line. But representing that they're connected together is kind of difficult. I mean, I suppose I could do an arrow. I'd have to have an arrow to show that which one comes first and which one comes second, because the order does matter. But that would get very clustered very quickly. So a man by the name of René Descartes developed something called the Cartesian coordinate system. And what he said, what he did, was he took that number line. I'm trying to get that actually straight. It's a little bit closer. And then he took a second number line, only he stood it up vertically, going through the 0 point of the first one. Now the first one was just standard, positive on the right, negative on the left. This vertical one he did the same thing with, except positive goes up. And negative goes down. And this horizontal axis, the first number line, was the x-axis. Again, in data analysis, that would be called the independent axis. And the vertical one was called the y-axis, or dependent axis. Where the two of them crossed here, which is the 0 point of both of them, It's called the origin. Because if you think of things starting at 0 and working out from there, that's where both of them start. That's where both of them originate. So to plot my point 2, 7, well, 2 would be an x value, that'd be about here. 7 would be a y value, that's about here. To show them linked together, you put a single point out here in space, its shadow falls on the 2 for the x and on the 7 for the y. So that is the point 2, 7. So what would that point be? There's a 4 here and a 3 here. Which one comes first? 4. So 4 comma 3. What would this point be called? You got the right idea. Keep going. Negative 6 and 4. There you go. So negative 6 comma 4. Yes, the horizontal, the x-axis has to come first in that ordered pair. What's that point going to be called? Negative 3, negative 5. Very good. And how about that point? 2, negative 4. Good. So we can identify these points on the graph. This is what we would refer to as the first coordinate, or quadrant, quadrant 1. And you see that the axes divide the graph into 4 sections called quadrants. This one is the second one, quadrant 2, quadrant 3, and quadrant 4. Now let's be a little trickier here. What would this point be called if I put one right there, right on the x-axis? Three, comma, 0. Since the x-axis goes through the 0 point of the y-axis, anything on the x-axis has a y-coordinate of 0. So this would be the coordinate what? Negative 7 comma 0. It's at negative 7 on the x-axis, and since it's on the axis, y is 0. How about this point right here? 0, 2. Very good. Or this one? 0, negative 4. Real good. So we need to be able to put points on the graph. And I'm going to combine a couple of things together here. What is the graph useful for anyway? Well, we've had equations like this. 7 equals 3x minus 2. How did we solve that? Add 2. 9 equals 3x, and then divide by 3. 3 equals x. Related to that one is this one. How do we solve it? We would add 2, 15 equals 3x, and then divide by 3. We solve it the exact same way. Why do we get a different answer? That number was different, right? So what if I have this? How am I going to solve it? add 2, and divide by 3. Take a different answer again because this number is different. I could create an infinite number of equations of that form that have this on the right side and different numbers on the left. And they're going to give you a different value for x. Well, they're called a family of equations, and we can represent all of them like this. Y equals 3x minus 2. To represent their solutions, well, we can represent some of their solutions in a table. Now let's pick values for x and figure out what y has to be. Let's say x is -3. How do we figure out what y has to be? Well, we replace x in this equation with -3. So it's 3 times -3 minus 2. 3 times -3 is -9 minus 2 is -11. So when x is -3, y is -11. How about if x is -1? Well, again, we replace x with -1. So 3 times -1 minus 2. What's 3 times -1? -3 minus 2? -5. So when x is -1, y is -5. I'll throw you an easy one. How about when x is 0? Well, it's going to be 3 times, replace x with 0. So 3 times 0 minus 2. What's 3 times 0? 3 times 0 is 0 minus 2 is -2. You're correct. So when x is 0, y is -2. How about when x is 1? It'll be 3 times 1 minus 2, which is yeah, 3 times 1 is 3, minus 2 is 1. When x is 1, y is 1. And if x is 3, it's 3 times 3 minus 2, which is 7. What's all that mean to us? These are ordered pairs on our graph. If x is -3, y is -11, is the ordered pair -3, -11. So we go -3, -11. So there's 1 point. Here, if x is -1, y is -5. It's -1, -5. There's a point right there. Here, if x is 0, y is -2. Where's that one going to go? Tell me from here. Do I go side to side, up, down? Where do I go? Down 2. Right there. Perfect. This is saying if x is 1, y is 1. That one's easy to find. And this one's saying if x is 3, y is 7. 3, 7, right there. Does that all make sense? Okay. Well, we're going to take our break here before I don't want to start another example quite yet. We'll come back at 4:28 and we'll start up again.